In the electrostatics example, it says a scientist describes an electrically neutral atom with a model that consists of a nucleus and a point particle with a positive charge Q. So what that's referencing is that's your nucleus. And the nucleus has a charge of plus Q. It's at the center of the atom, and electron volume charge density given by these equations here. Once I reach a radius of alpha, then the charge density would hit 0. To translate this, what's happening is let's let this purple dashed line represent the boundary of the atom. And really what it's saying is once I get beyond alpha, radius alpha, the total charge is 0. So if I were to draw a Gaussian surface that's external of this purple line, my Gaussian surface would tell me that the Q enclosed is 0. Now, before that, if I were to draw a Gaussian surface inside, the Q enclosed would be greater than 0, but it would be less than positive Q. Sorry about that quick slip. So, the first question, A, asks us, well, what does the charge quantity look like by a Gaussian sphere of just the nucleus? And then what does it look like of just the electrons? So, just the nucleus? It's simple. The nucleus, as it says in here, point particle, that indicates it's constant, and it's constantly plus Q. Now, as for the electron, once I hit the position radius alpha, the total charge by the electrons would be negative Q, because the electrons would cancel out the positive Q from the nucleus. So what I can say is, at least this portion of the graph is horizontal. Well, what happens before? Well, if I am at the nucleus itself, I have enclosed 0 electrons. So I would not have any electron charge. Yet I end up here where I have an electron charge combined of minus Q. According to this equation, between 0 and alpha, basically when I'm less than alpha, I have an exponential decay equation. So the equation would decay like so. Let's go ahead and take a look at part B. So part B, C and D, I'll copy this and paste it over. Part B says the dash curve on the graph below represents electric field, blah, 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 information. So where do we go from here? So this dotted line is showing the electric field created just by the nucleus. And we need to sketch in, well, what happens if we include the electron clouds? Basically, once I hit alpha, the charge enclosed is 0. So we're done. Now, over time, what would happen compared to the electric field created by just the nucleus, if I include the electrons, that means my line should be, below what it would be if it was just the nucleus. The reason being is the closer and closer I get to the middle, the less and less influence the electrons have on the electric field, because according to Gauss's law and my Gaussian surface, they're not enclosed. As I move farther and farther away from the nucleus, get closer and closer to alpha, more and more electrons get enclosed and eventually cause the field to plummet to 0. And the reason why it plummets to 0 is because once I've hit alpha, the enclosed charge is 0. Now part C is going to ask, using Gauss's law, derive an expression for the electric field due to the neutral atom for the following positions, and base it off of Q, alpha, beta, and R. So when R is greater than alpha, That one's fairly simple. When r is greater than alpha, the field is 0. So we'll put in equals 0. Now let me zoom out. For C2, this is going to get a lot more complicated. Let's go right into Gauss's law. We're going to focus in Gauss's law on the negative charges. So the Q negative at any point is going to be the integral of that charge density that they gave us, dV. So Q negative will be the integral, which we'll take from 0 to some value r, because we want to know at any point r, not necessarily alpha, but at any point r. The equation is negative beta over r squared e to the negative r over alpha as given, and then dV. So dV is going to be the surface area of the sphere, 4 pi r squared dr. And now we can do the integral with respect to r. This r squared cancels with this r squared, and I'm going to be left with a 4 pi beta that's going to come outside of the integral. So Q negative is 4 pi beta. I'm going to take the integral from 0 to r. And we are left inside with a negative e raised to the power of negative r over alpha dr. Now, let's take that integral. When I take the integral of this fun, happy stuff here, I'm going to produce a negative 4 pi beta. 4 pi beta is my constant. I got the negative alpha, negative e to the negative r over alpha, and I'm taking from 0 to r. So if I go to resolve this integral from 0 to r, so we're almost there. We need to go back to Gauss's law right here. We have that Q enclosed. We have the negative Q enclosed. And that's an important thing to remember as I finish off this problem. So EA equals that Q enclosed over epsilon naught. The Gaussian surface, since it is a sphere, it's going to have a surface area of 4 pi r squared. Q enclosed will equal plus Q from the nucleus, and then what I just solved right here, which is 4 pi beta alpha e to the negative r over alpha minus 1, all of which is divided by epsilon naught. Looks like a lot of stuff, because it is. The electric field, as I divide the 4 pi r squared over, that'll be 1 over 4 pi r squared epsilon naught. Remember, 1 over 4 pi epsilon naught is k, and then you have the r squared because it is a sphere. And this is going to be over 1 because I moved the epsilon naught over here. And then I just take my numerator from before, 4 pi beta alpha e to the negative r over alpha minus 1. Whew, that was brutal. Question D, fortunately, is a very short one. I kind of already answered it. It says, based on the model proposed by the scientists, what does alpha actually mean? And that comes back to the very first thing I told you about. Alpha is the radius of the electron cloud. Once you get beyond alpha, you're no longer in the atom.